Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The intellectual firmament of European physical science in early 1820 possessed a satisfying, if ultimately fragile, symmetry. The universe of forces appeared to be governed by a Newtonian paradigm, a clockwork of actions at a distance, described by elegant inverse square laws. Charles Augustin de Coulomb had provided two such laws, one for the forces between electric charges and another, entirely distinct, for the forces between the poles of magnets. Electricity and magnetism were separate, well-behaved domains, their phenomena catalogued, their mathematics established. It was into this stable world that Hans Christian Oersted's discovery on the 21st of July, 1820, landed with the force for profound anomaly. The simple demonstration that a wire carrying an electric current could deflect a magnetic compass needle shattered the conceptual wall between the two fields. It was an observation of immense consequence, a qualitative revelation that demanded a quantitative explanation. The news reached the Académie des Sciences in Paris on the 11th of September, and among the assembled luminaries, it was André-Marie Ampère who would seize upon this disruptive fact and, with astonishing speed and intellectual power, erect from it a complete new science. His endeavour culminated in his 1826 masterwork, the Mémoire sur la théorie mathématique des phénomènes électrodynamiques, uniquement déduit de l'expérience, a text that represents one of the most remarkable and swift syntheses in the history of physics. Ampère's intellectual inheritance positioned him, uniquely for this task. He was deeply embedded in a French Laplacian school of physics, an approach championed by Pierre-Simon Laplace that prized the reduction of all physical phenomena to forces acting centrally between point-like particles, varying with some function of the distance separating them. This program was deeply Newtonian in spirit. Upon hearing of Oersted's result, Ampère's contemporaries, Jean-Baptiste Biot and Félix Savart, immediately began their own experimental investigations. Within weeks, they formulated an empirical law describing the force exerted by a long, straight current-carrying wire on a single magnetic pole. Theirs was a hybrid law, a useful but conceptually incomplete bridge between the new phenomenon and the old physics of magnetism. Ampère, however, pursued a far more radical and ambitious path, influenced by Laplace's direct encouragement to seek a fundamental inverse-square relationship. Ampère formulated a foundational axiom of breathtaking simplicity and power. Magnetism itself is an illusion. He proposed that all magnetic phenomena are merely the result of electricity in motion. The permanent magnet, in his view, was a body containing a multitude of microscopic perpetual electrical currents, which he termed molecular currents, circulating within its substance. This conceptual leap was profound. It promised a unification, erasing one of the fundamental forces from the ontology of physics and recasting it as a manifestation of the other. His task, then, was to discover the fundamental law of force acting between two elements of electrical current. To achieve this, Ampère demonstrated a genius. It was both experimental and theoretical. He understood that to isolate the pure interaction between currents, he needed to eliminate the confounding influence of pre-existing magnetic fields, including the Earth's. He devised the astatic needle, a clever arrangement of two parallel magnetic needles with opposing polarity, which rendered the system largely immune to the terrestrial magnetic field, allowing the faint forces between wires to be observed with clarity. His experimental program was a model of systematic, logical deduction, designed to progressively determine the mathematical form of the force law through a series of four exquisitely designed equilibrium, or null, experiments. These experiments were designed so that no force was produced, a condition that provides more powerful constraints on the form of a law than a simple measurement of effect. The first experiment established that reversing the direction of the current in one of two parallel wires reversed the force from attraction to repulsion, demonstrating the force's dependence on the relative directions of the currents. The second, more subtle, experiment showed that a sinuously bent wire produced the same effect on a parallel wire as a straight wire would, provided the endpoints were the same. The implication was immense. The force was a vector sum of the forces between infinitesimal elements of the current. The overall shape of the circuit was irrelevant except as the boundary of an integration. This licensed the entire enterprise of creating a differential force law, a force between one infinitesimal current element, its length written as ds, and another, ds prime. His third experiment involved the interaction between geometrically similar circuits of different sizes. He demonstrated that the force between the circuits was independent of a uniform scaling of the entire system, as long as the currents remained the same. This crucial result led him directly to the conclusion that the force must vary as the inverse square of the distance between the current elements, a vindication of the Laplacian program and parallel to the gravitational and electrostatic. The fourth and final null experiment was the most mathematically complex. It involved the equilibrium of a circular wire element able to rotate around a specific axis, while under the influence of two other circuits. Its purpose was to determine the precise angular dependence of the force between two arbitrarily oriented current elements. From these four experimental pillars, Ampère derived his celebrated force law, voiced in prose. The law states that the differential force between two infinitesimal current elements is proportional to the product of the current intensities, I and I prime, and the infinitesimal lengths of the current elements, ds and ds prime. This product is then divided by the square of the distance, r, separating them. The entire expression is multiplied by a complex geometric factor involving the angles that the two current elements make with the line connecting them. Specifically, it involves the cosine of the angle between the two current elements and a term proportional to the product of the cosines of the angles each element makes with the line joining them. This was a force law of a new kind. It was a central force, in keeping with his Laplacian background, yet it depended on orientation in a way Coulomb's and Newton's laws did not. It was the mathematical core of his new science, which he christened electrodynamics to signify the primacy of currents in motion, distinct from the static science of electrostatics. The immediate application and proof of this new framework was the solenoid. Having postulated that magnets derive their properties from internal molecular currents, Ampère constructed a macroscopic analog, a Hegel coil of wire. He then demonstrated, both through calculation using his force law and through direct experiment, that this solenoid behaved exactly like a bar magnet. It had a north and a south pole. It would align itself with the Earth's magnetic field, and two solenoids would attract and repel each other just as two bar magnets would. This was a triumphant moment of synthesis. He had started with the abstract hypothesis that magnetism is electricity in motion, derived a fundamental force law from first principles and experiment, and then used that law to construct an artificial object that perfectly mimicked the behavior of a natural magnet. The publication of his full memoir consolidated these findings, presenting the science of electrodynamics to the world as a complete, axiomatic, and experimentally verified system. It was a towering intellectual achievement, conceived and largely completed in the span of few years. The reception of Ampère's theory was complex, while its mathematical elegance and predictive power were widely admired. Its foundational philosophy encountered resistance. The competing Biot-Savart law, while less fundamental, was often seen as more practical for certain calculations and remained in use. The most significant intellectual challenge, however, came from the contrasting vision of Michael Faraday in London. Faraday, a brilliant experimentalist with a different kind of physical intuition, found Ampère's concept of action at a distance deeply unsatisfying. Where Ampère saw an abstract mathematical force acting between distant current elements in a void, Faraday visualized a space filled with lines of force, a physical field that mediated the interaction. For Faraday, the energy of the system resided in the space surrounding the wires, a tangible medium, a concept wholly foreign to Ampère's Newtonian framework. This represented a profound schism in physical thinking. It was a debate between a physics of particles and forces, and a nascent physics of fields and energy. It is a quiet irony of history that Ampère, the far more sophisticated mathematician, championed a conceptual framework that would eventually be seen as a classical holdover, while Faraday, with his pictorial, almost non-mathematical approach, was laying the intuitive groundwork for modern field theory. Despite this philosophical divergence, Ampère's work became a cornerstone for future developments. His formulation of the force between current elements proved more general and ultimately more fruitful than the Biot-Savart law. The German physicist Wilhelm Weber-Liter extended Ampère's work, developing the velocity-dependent force law to encompass a wider range of electromagnetic phenomena, building directly upon the action at a distance framework. The mathematical nature of Ampère's law, with its complex directional dependencies, also proffered the need for a more sophisticated mathematical language. The exterior algebra developed by Hermann Grassmann in the 1840s, though largely ignored at the time, would prove to be the ideal mathematical structure for expressing such relationships. Ampère's complex angular factors find their most natural home within the wedge products and differential forms of modern geometry. The ultimate inheritor and transformer of Ampère's legacy was James Clerk Maxwell. Maxwell began his own monumental work on electromagnetism by explicitly seeking to translate Faraday's intuitive field concepts into a rigorous mathematical language. In doing so, he drew heavily upon the quantitative foundations laid by Ampère. One of the four pillars of Maxwell's unified theory of electromagnetism is, in fact, a direct descendant of Ampère's work, now known as Ampère's circuital law. This law, in its modern integral form, states that for any closed loop, the line integral of the magnetic field vector around the loop is proportional to the total electric current passing through the surface enclosed by the loop. Maxwell's great insight was to add a second term, the displacement current, proportional to the time rate of change of the electric field. This addition completed the theory, predicted the existence of electromagnetic waves, and unified electricity, magnetism, and light. Yet, the correlationship between the magnetic field and the source current, the foundational idea that currents create magnetic circulation, is a direct inheritance from Ampere's electrodynamics. The mathematical formalisms later developed by Oliver Heaviside and Josiah Willard Gibbs, who recast Maxwell's original equations into the more compact vector calculus we use today, further clarified these relationships, but the physical insight traces its lineage directly back to Paris in 1820. In final analysis, André-Marie Ampere's mathematical theory of electrodynamic phenomena stands as a singular monument to the power of theoretical vision combined with experimental rigor. Presented with a bewildering new physical effect that overturned the established order, he declined to simply catalogue it. Instead, he advanced a revolutionary, unifying hypothesis, that of molecular currents, and pursued its logical consequences with relentless determination. Through a sophisticated program of null experiments, he deduced a fundamental force law of a completely new character, one that was both Newtonian in its inverse square form and novel in its complex dependence on the geometry of currents. He single-handedly founded the science of electrodynamics, giving it a name, a foundational law, and a stunning experimental vindication in the form of the solenoid. While the action at a distance philosophy that underpinned his thinking was eventually superseded by the field theory of Faraday and Maxwell, the mathematical substance of his work anent the relationship between electric current and magnetic force was absorbed wholesale into the new paradigm. It became a permanent and indispensable part of the bedrock of physics. Ampere's achievement was to take a spark of discovery and from it construct a coherent, quantitative, and predictive theoretical edifice, demonstrating that even the most startling new phenomena could be rendered intelligible through the disciplined application of mathematical reason. His work remains an enduring masterclass in the creation of physical theory.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.